when I learned about planets, that basically shifted the trajectory of my entire life. Now, right now, we know that there are very close to 6,000 exoplanets. You can see here in the top left. This is the NASA Exoplanet Archive, by the way. You can visit this website anytime that you want. Like all of the newest information about exoplanets, you can find publicly available here. And I don't know, we'll probably eclipse the 6,000 number in, who knows, like maybe a month, maybe a few months. So this is very cool. Now, like I said, I used to play football. You can see a little version of me with more hair on the left. And I got a scholarship to play at the University of Kentucky, which you can see right here. This was actually the week before I had a career-ending knee injury. And, you know, the academic tutors and stuff, they would always tell us, you know, you could always blow your knee out. And, you know, 18-year-old me, that kind of goes in one year and out the other. But little did I know that one day I'll become an astrophysicist because I blew my knee out. So I redid school, kind of started from scratch, started from the bottom, went to community college, did undergrad, and then recently completed grad school. And now I like to talk about exoplanets, science in general, really anything that anybody wants to hear me talk about, I'll pretty much do. So exoplanets are interesting because we've only recently been able to detect them, but we've suspected that they've been around for a long time. And that suspicion goes back suspiciously far. In the 1500s, like the mid-1500s, there's the person that I consider the first exoplaneteer, which is what I consider people who study exoplanets. This is a guy named Giordano Bruno. He was a member of the Vatican, kind of. He was like a heretic because he believed that planets orbited stars and that there was life on other planets. And here is a quote that I think is really succinct and sort of impressive that Giordano made. He says, "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our solar system." Remember, back then we hadn't found Uranus or Neptune yet, or we hadn't found Neptune yet. Then he says they remain invisible to us because they're smaller and non-luminous. And this is exactly right. This is exactly why we can't see other planets. Exactly why they didn't know it back then. He had no evidence to believe this. There was like no reason for him to think this, but he was spot on. He was exactly right. And of course, for his premonition, he was executed for heresy by the church. Mm-hmm. But he went out with a bang. He stood on business. He says, at the end, take comfort, for the time will come when all men see as I do. Here we are 500 years later, and indeed, he was right. Okay, so now, astronomers are thinking about planets, thinking about exoplanets. What would we expect to find? In astronomy, it kind of makes sense to assume that you're very average, that you're run-of-the-mill. You know, the universe is enormous. Most things are average, and it would make sense to assume that our solar system was just completely average. So when we started looking for planets, we thought that we would find something like this. You know, our solar system is very ordered. There are 4 rocky planets that are close. There are 4 gas planets that are farther. Everything pretty much orbits in the same plane. It's very nice. It's very, very orderly. Of course, then there's Pluto, which is a lot smaller. You can see it's a little bit larger than Alaska in diameter. And it has this really wonky inclined orbit. So it doesn't really fit in. And astronomers come up with a very elegant solution to say it's not a planet. So our solar system is now orderly again. Now, the naming convention that we use for planets is terrestrial planets or Earth-like. And this can be, I think, a little bit misleading because when you hear Earth-like planet, or rather when I first heard Earth-like planet, I'm thinking a planet that's like Earth, but that's not at all what it means. It really just means that it's about the size of Earth. And not even exactly the size of Earth, just kind of roughly the size of Earth. Next, we have the Jupiters, which are true gas giants. So these are going to be larger than Uranus and Neptune, which we would call the Neptunes. So lots of reusing of names, really, based on the planets that we already know about. Now, one interesting dividing line in our solar system is what is called the snow line or the frost line. And it separates the larger planets from the smaller planets. And this tells you something about how we used to, about how we began thinking about planet formation. If you get further and further out in the solar system and it's colder in material that would usually be a gas when it's close to the star can freeze and condense, then you sort of have more stuff to work with, right? A block of CO2 on Earth is going to be gas, but a block of CO2 out beyond Saturn will be a solid. So you can make larger planets just because you're condensing more ices. So what we expected to find were large gas giants that are further away, and then smaller rocky planets that were a little bit closer. And the first planets that we found were completely surprising. They're actually called the pulsar planets in 1992. If you don't know what a pulsar is, a really massive star at the end of its life sort of runs out of fuel at once and collapses. And the collapse is so intense and so violent that there's this ricochet that causes a supernova explosion. And what's left at the core is a neutron star, sometimes a black hole, depending on how massive the star was. And at the very least, you would expect an explosion like this to obliterate any planets that were nearby. But the first planets that we found are actually orbiting a pulsar. So this is interesting. This is, if you were to have asked any astronomer at the time if there were planets orbiting pulsars, I don't think anybody would have suspected that. Maybe some like crazy theorist who was trying to prove a point or make a name for themselves. But in fact, that is where we found the first planets. I'm still skeptical that a planet could survive a supernova explosion. They may be able to, but there's also this like idea that planets could reform. Like there could be a second round of planet formation in the material that has been, mashed up and even created in the supernova. But that's a different story. I guess an interesting note is we found 3 pulsar planets in 1992, and since then have only found 3 more. So you may have thought that because you found it early, these are easy to find or common, but that doesn't really appear to be the case. At any rate, in 1995, we found the first exoplanet around a sun-like star. This is 51 Peg b, and it's a hot Jupiter. So again, not what we would expect if we were relying solely on our solar system as the standard for planets out in the galaxy. Now, to this day, it's not really easy, or it's not completely agreed upon how you could get a planet like this. Like the intuition that you can build more massive planets further away from the star still holds. So how do you get these hot Jupiters, these massive Jupiter-like planets that orbit in just a few days? And there's really 2 leading theories. One of them is that they could potentially form nearby under the right conditions. So that would be the example down here in the bottom left, where a Jupiter-sized planet just starts off right next to the star. Over time, the disk clears out and you're left with a hot Jupiter. But another is that these planets actually may need to form further away. And over time, due to gravitational interactions, they lose some angular momentum and have their orbits circularized. So after a few million years, or tens of millions of years, or maybe a few billion years, you kind of end up with these hot Jupiters that migrate over time. So very interesting. Then, when we started finding those hot Jupiters right away, it kind of seemed like, well, if a Jupiter-sized planet could migrate all the way into its star, maybe the migration process is so efficient that we wouldn't expect to find that many small rocky planets near stars. And the next big discovery we made was, in fact, that the most common planets in our galaxy that we can detect are these small planets that are called super-Earths and sub-Neptunes. So you can kind of see what I think is cool to point out, that in exoplanet science, we go through this iterative process where we're taking the very limited amount of data that we know, what our solar system looks like, what are the first planets that we find, and then we extrapolate. And then when we do a better job searching, realize that we were extrapolating from a small number of data points, which is like something that I guess in your life and in science you should be careful not to do. So this is really interesting. Now we have an idea of what the 6,000, I'm going to say, easiest planets to find look like. Here's a plot, and I want to build out this context plot so you can get a really good idea for what types of planets we know for sure exist and how they kind of differ from what we have in our own solar system. So here on the x-axis, we have orbital period in days. Over here on the right would be 100, so this would be like a third of an Earth year, and 365 isn't quite on the plot. And then on the y-axis, we have planet size, and this is in Earth radii. So at the bottom, you would have a planet that was 70% as large as the Earth, and at the top, you'd have a planet that was 16 times as large. So, going to add in a couple of reference lines. You can see where Saturn, Neptune, Earth, and Jupiter exist here. So you already see that Earth is near the bottom. In terms of the planets that we know about, Earth is pretty small. Next, I added in Mercury, which is the vertical line here on the right. And Mercury has an 88-day orbit. So you can already start to see that we're finding tons of planets that are much closer to their stars than any of the planets are to our sun. Mercury is kind of like on the outer edge of the plot of known exoplanets in terms of orbital period. And the top left, you see the hot Jupiters. I heard Jesse talking about them in the talk before, and I'll talk about them a little bit more. But there's definitely a class of hot Jupiter planets that we know about. They're easy to find, they're large, they're massive, they leave their imprint on their systems. And here, interestingly, there is this population of super Earths and sub-Neptunes. And you can tell that they seem to be distinct. Like there's clearly two different populations as opposed to just one big normal distribution, which maybe is what you would think would happen, that, why is nature like preferentially making planets either a little bit smaller than Neptune or a little bit larger than Earth, but almost never the size in between? We'll talk a little bit about that, a little more about that later. So here we have our solar system, which again, we always have been using as the standard here. And you realize that the most common planets in our galaxy, again, that we can detect, are actually completely missing from our solar system, right? We have Earth and we have Neptune, but most planets are somewhere in between those two. And that's still a bit of a mystery for our solar system. Why are we not average? Like, what happened in the development of our solar system that causes it to be an outlier? Or are we just so limited in our ability to detect these other systems that we haven't really got the sensitivity to make a robust statement about how rare our solar system actually is? So one idea, I don't want to leave you just completely hanging there, an idea that seems compelling to me is that when you get a planet like Jupiter, this really massive gas giant planet, what it can do, and this should make sense, heuristically, is it can kind of choke off the ability for other planets to grow. A large planet gets more massive, which allows it to eat up more material, which makes it more massive, which allows it to eat up more material, and you get this like runaway effect. And any other planets that are hoping to form and grow are just sort of running out of material. Jupiter's draining the pool, and there's just no other material for the planets to form from. And I think that is probably on the right track. It's a bit more complicated, but you can imagine here as you look at this diagram, in the top panel, Jupiter gets a head start. So Jupiter starts eating things up, and planets in the inner solar system start forming. But the planets that are on the outer inner solar system, which would be Mars, and the inner solar system, which would be Mercury, which is basically sandwiched between Jupiter and the Sun, are smaller because they had less stuff. You have a star to your left and a gas giant to your right. And in the middle there, you get Venus and Earth, which were able to grow a little bit bigger. I think that this is a pretty compelling general image for maybe what happened in our solar system. Jupiter just sort of hogged what the other planets needed, which maybe is why we even exist on Earth at all. Maybe that's why we have life. So, on this demographics plot, I think what's interesting, besides what we do see, is what we don't see, like what's missing here. We clearly can detect hot Jupiters. We clearly can detect what I'm going to call hot super Earths, which are these planets in the bottom left that are close to their stars. Nobody calls them hot super Earths, I don't think, but I did. I just made up my own name. But there doesn't seem to be any hot Neptunes. Why? Why is nature making hot Jupiters and then hot Earths, but not hot Neptunes? Very good question. And then the other feature I want to highlight is what's called the radius gap. And it's this split in radius between the super Earths and the sub Neptunes, this dividing line. This is what a lot of my PhD research was, trying to understand how planets evolve to give us this distribution that we see. So we can explain both of those scarce regions, the lack of hot Neptunes and the lack of planets in between super Earths and sub Neptunes, by this process called photoevaporation. So you don't need me to tell you that stars are hot. They're hot because they're putting out tons and tons of electromagnetic radiation. Some of it we can see, much of it we can't because it's really high energy, like X-rays. So X-rays do something to gas, they energize it. And if it gets enough energy, it can escape from the planet. So early on in a system, we could imagine that there actually is some normal distribution of baby planets that are born that are roughly the same size, let's say. And over time, the energy from the star, this XUV energy from the star, it bakes away the accretion disk that makes the planets. So the gas leaves at some point, and then you just start with wherever the planets are in that formation process. And some of that radiation is going to hit the planet. Whoops. That was not an ad for HP. Unless HP wants to pay me. Okay, so I mean, what happens to gas when you heat it up? Anybody? Oh, and feel free to ask me a question if you want throughout any of this. What, somebody said it? Expands, yes, expands. The same thing happens in space, right? Like physics is physics, heat it up, it expands. If it expands beyond the region where the planet is massive enough to hold on to it, then it just gets lost into space. And if you do that over time, the planet is literally losing mass. It's called atmospheric mass loss. And with every bit of mass the planet loses, it also loses its ability to hold on to future gas that's expanding. So you can kind of see like it's the opposite of a formation thing, where as you lose more mass, you lose more mass more quickly. And this is what's happening with planets. If you do this long enough, then you'll end up with maybe a planet that started out looking like Neptune, that when we look at it, looks like a rocky core, what we would call a super Earth. Now, here's an animation of what that looks like in the context of the radius gap. So let's see. Start it over, right? So you see this, imagine that the planets up top, these are the sub-Neptunes, the planets down below are the super Earths. And I want you to pay attention to this time scale here. So we're looking at like the first 300 million years. In astronomical terms, a star is a baby for 300 million years. So this is a very, very, very young system. And you can see how the XUV radiation is very intense over that period. So if you pay attention to the highlighted planet, over time, it gets smaller and smaller. And that process slows down as the star begins to mature. And eventually, there comes a point where the radiation from the star is no longer enough to significantly affect the mass. So, you can imagine us starting with a planet that maybe had a little bit less atmosphere, and it would have quickly moved from the sub-Neptune regime down to the super Earths. Okay, so this makes a little bit more sense. These hot Neptunes that we don't see are there in the beginning, but they just don't survive because they're too close to the star and they're not massive enough to hold on to their atmospheres. The hot Jupiter planets are because they're more massive. So they just are strong enough in a gravitational sense to evade complete erosion. Now, how do you study this process? I know that I said that it takes about 300 million years, which sounds like a long time, but the universe is like 14 billion years old almost. So it's actually a relatively small amount of time. So at any given time that an alien civilization builds telescopes and looks out, they're actually probably going to see a system that's mature and not a system that's young. So it's hard to detect this in real time. But what we can do is we can study these hot Jupiters. They're massive enough that they'll never fully lose their atmospheres, but they still should be losing some of their atmospheres. This is kind of like how you test this theory of photoevaporation out. And this was my first research project in my PhD. I was looking at this hot Jupiter called WASP-69b. This is to scale, so you can see it's pretty big compared to its star. It's about 30% the mass of Jupiter, but 10% larger than Jupiter. So if you think about that, Jupiter, which is already a pretty low dense planet, right? It's a gas giant. And this one is puffed up even more, and that's because it orbits in just about 4 days. So, you park a bunch of gas right next to a star, it's going to heat up and expand. And ideally, we can capture some of that gas escaping and see if we really understand the physics behind how these planets are evolving. This is an animation that came out with the paper when we finally published it, and we were able to detect not only gas escaping from this planet, about 200,000 tons per second, which is a lot, but it also is having that gas stretched out into a tail, not unlike a comet, that is about 350,000 miles long. So many times the length of the planet itself. And this is really a remarkable detection to make so far away, and tells us something about the interaction between stars and planets. So a really cool thing, this caught on and kind of made international headlines. And I was very proud that somebody wrote a clickbait article on it. And here you can see it. Scientists find a planet with a tail 150 times longer than the Mississippi. That didn't sound right to me at first. So I looked up the length of the Mississippi River and I did the conversion, and they got it exactly right. It's about 150 times longer than the Mississippi. So it's not a super helpful unit, but I respect the conversion nonetheless. This was a journalist that knew what he was doing for sure. Okay, so we know that there are these hot Jupiters, and we know that they expand. We know that smaller planets that have gas do the same thing. And there's this other mysterious and still inexplicable, to some degree, group of planets called superpuffs. So here you can see a couple of the more famous ones in the Kepler-51 system. Now, what's interesting about these planets is that they all have densities that are really close to cotton candy, like the carnival food, cotton candy. The overall mass and the overall size of the planet gives you a density that's comparable to this like wispy cotton candy that's almost nothing. Here you can see on the bottom some of the solar system planets, the Earth there. The 3 planets on top are roughly twice as massive as the Earth, but they're like many times larger. So, typically you would expect a planet the size of Kepler-51c or Kepler-51d to be as massive as Saturn or Jupiter, like 100 times more massive than the Earth, or 300 times. But these super puff planets, they're inexplicably low mass for how large they are. We don't really know why, but they're always orbiting really young stars. So Kepler 51 is a really young star. I'm pretty sure that what's happening is you just have a bunch of gas that's puffed up, and you're sort of seeing an unrealistic snapshot of the planet when it's a kid, like in a really awkward phase. I don't know. You look at like your high school, or what's the awkward age? I don't know, like middle school or something like that. Maybe you had a weird haircut or whatever. And I think that that's what we're sort of seeing right now with these super puff planets. Now, another really interesting class of planet that I'm sort of obsessed with is called water worlds. Now, when you hear water world, you may think of a planet that's sort of like Earth, that's really just covered in a bunch of water. You know, what they say Earth is 75% water, right? The surface. And that's true. Earth's surface is 75% water, about something like that. But, you know, if I just poured water on 75% of the surface of this podium, you wouldn't say that the podium was 75% water, right? It's almost no water. And that's actually what the Earth is like. From an exoplanet research perspective, there's barely any water on the Earth. It makes up like 0.05% of the total mass, or something like that. But there seems to be planets, which we call water worlds, that are much more water than we have here on Earth, like 20% or 50%. Some cases even more, which is really interesting, because when you get a planet that is considerably comprised or composed of water, the water at depth starts to behave funny. It sort of compresses into a solid, but it's not like a cold solid ice that we have, sort of a hot ice in these exotic gas phases. And you can see an example here on the left of the difference between a water world and an Earth-like planet. GJ 1214b is just like a notorious strong candidate for a water world. It hasn't really been proven yet beyond a shadow of a doubt, but you can see that it's just a lot larger than the Earth. And whereas the Earth is less than a fraction of a percent water, a planet like this water world is maybe 50% water. Now, it probably isn't just H2O, maybe it's like other volatiles, carbon dioxide, that sort of thing. But I think that these water worlds are super interesting and compelling to think about, especially when it comes to life. We assume that life needs water, which feels like a safe assumption, but these water worlds are so different than what we have in our oceans here on Earth that I'm not sure exactly what that would look like. Maybe it's a little bit more complicated than it sounds. Okay, so we've got this really interesting class of water worlds that we're trying to figure out. There are these like hard to explain super puff planets. We got hot Jupiters, sub-Neptunes, and super Earths. But we also have the ability now with JWST to probe the atmospheres of planets and see if there are biosignatures, or at least what we would call biosignatures, Earth-like biosignatures. And we have tried to do that with what I think is one of the more interesting solar systems out there, the TRAPPIST-1 system, which maybe you've heard of, has 7 roughly Earth-sized planets. Some of them are closer to the size of Earth. Some of the other ones are closer to like super Earths, maybe a sub-Neptune in there. And what we can try to do, as long as you have a good enough, a sensitive enough telescope and detector, is somebody I'm sure today has talked about the transit method, where you kind of stare at a star and then you know that there's a planet because it blocks out a little bit of light. And based on the amount of light that gets blocked, you know how large the planet is. But when that happens, an exoplanet transit, some of the light gets blocked out by the planet. This is our planet. Some of the light gets blocked out by the planet, but some of the photons go through the atmosphere, right? And then just come on to us. So this tells us what's in the atmosphere. So if there was methane and CO2 and H2O and whatever other things that we have here on Earth in the atmosphere, it wouldn't necessarily mean that there was life on the planet, but it would be evidence that there could be something like Earth-like life on the planet. And so this may be one of the ways that we are able to first say that we find life. And we tried to look at the atmospheres of these TRAPPIST-1 planets, and basically all of the observations so far have come back and said that they don't have atmospheres. So you could kind of think of them as just completely stripped or completely bare. But personally, I'm not totally convinced because it doesn't seem like we can detect a small atmosphere yet. Like, sure, they're not gas giants that have these enormous inflated atmospheres, but we don't have any detections of what I call a thin atmosphere. And you can kind of see it here. You know, we think of the Earth as having a pretty substantial atmosphere, right? Like we all breathe it. You go up in a plane and come back, your ears are pounding. This happens to me. And it's because there's so much atmosphere sitting on top of your head, basically. Well, if you see the Earth from space, you can see that the atmosphere is really paper thin. Like, it's not a substantial atmosphere. As an exoplanet researcher, I would say that this planet doesn't have an atmosphere. And until we can detect a planet that has like a thin atmosphere, sort of like we have here, I think it's hard to rule out that those planets, these TRAPPIST planets, don't have atmospheres, although that is what the JWST observation said. So I take everything with a grain of salt, including that. Now, the exoplanet outlook is really exciting, especially now that I think Congress did not accept the enormous NASA budget cuts, or it seems like they're not going to, which was going to like defund all of these really cool missions. And this is cool because, you know, we're getting technologically advanced such that we can start exploring more of the parameter space of exoplanets, right? We're not stuck to the planets that are closer than Mercury. Here you can see, basically in the red are everything that I've been talking to you about today. Planets that are mostly found with Kepler. There's a few other instruments that have done a really good job finding planets, but a lot of the planets that we know of are these red data points. And you can see that we don't have the ability to detect planets that are actually like Earth. Like, we've never detected a planet that orbited a star like the sun, that was the mass of the Earth and the distance of the Earth away from its star. I know that there's a lot of headlines that say that we found an Earth, and we've never done it. We don't have the ability to detect. If we were in another solar system, we could not find our Earth. We don't have that ability, but we will soon. This is a plot of simulated, predicted exoplanets that will be found by what used to be called WFIRST, now it's called the Roman telescope. So in the next decade or two, I think we'll be able to fill out the more interesting parts of the exoplanet demographics plots. So we should be able to detect planets like Jupiter, Saturn, Earth, Venus, Mars. I think another thing to point out, just so you can get an idea of how hard it is to detect an Earth-like planet, is that if, again, we were these alien astronomers and we were trying to detect a radial velocity signature from Earth, like we were trying to detect the motion that the Earth was causing the sun to do. Does anybody have an idea of what that velocity is? You know, as the Earth completes an orbit 365 days, I think it's moving at like 36,000 miles per hour or something. Does anybody know what speed the sun is moving at because of the Earth? This is what we would have to detect. So it's about 9 or 10 centimeters per second. So this is like the speed of one of those big Galapagos tortoises. And you're trying to detect that light years away. And if you can detect that, then you can detect Earth. And if you can't, then you can't. Mars, the number is even smaller. It's about 1 centimeter per second, which I think is like the speed of a snail. And it's like hard to imagine that we'll ever be able to detect from 50 light years away a star moving at a literal snail pace. But that's what you'd have to do to detect a planet like Mars. So That sounds pretty bleak, but we'll figure it out, I'm sure. A lot of smart people here. Maybe they'll use machine learning or something like that and be able to get our uncertainties down. So that's all I have. Hopefully you learned something interesting about exoplanets. Take any questions as well.
Just a couple of questions. I have a question for you.
Yeah.
Which of the new spacecraft that we're building to search for them are you most excited about?
The most interesting instrument to me is the Habitable Worlds Telescope. So this is going to be a space observatory that has a coronagraph, which allows you to block out the star and try to search for planets like by directly imaging them. So you're not looking for like a transit signal or a radial velocity motion. You're actually looking for a picture of the planet, and they say that they'll be able to detect an Earth size and Earth distance planet at a few light years or like within 30 light years or something. It always feels like everybody always says that they're going to be able to detect Earth, but we never do.
Well, we'll just have to wait a little bit longer. Maybe you'll be the one.
Yeah.
So, yeah. Anyway, let's thank our speaker again. Thank you so much.
Thanks.